Now let's look at one more example, and this time we're going to look at a two-tailed test. Here we have a driver's license test, okay, DMV test, and they are now considering a new test. So they want to make sure that the variance of scores that applicants score, the variance is similar to what they had previously in the old test. So the old test variance was 100, or so now they want to test whether the new test also has variance about 100, or is it different. So they took a random sample of 30 examination scores with the new test, and the sample variance turned out to be 162. Okay, it's variance. Now we want to test whether this hypothesis is true or not with an alpha of 0.05. So let's first define the parameters and the population, etc., and then we'll do the test. So population and the population variance, and what kind of hypothesis are we going to test, and what's the alpha value. So here we go. So sigma, we are testing whether sigma squared is equal to 100 or not equal to 100. Now what about the sample? So we have a sample size of 30 and 162 for the sample variance. So it's a good idea to color code the given values, and the so we'll have we'll know which values are given and which values are calculated by us. Now the test statistic is n minus 1, so n minus 1 times s squared sample variance. So here it is, sample variance is given, so we don't need to square this. If this was standard deviation, then we have to square it. Okay, same here, divided by the sigma sub 0 squared. So that's our test statistic, and the degrees of freedom is n minus 1. Now we'll do the test both using the test statistic as well as the p-value. So this is a two-tailed test, so we have two different chi-squared table values. The left side table value is given by chi-squared dot inv. Now the alpha value, okay, should be distributed to the two tails, so it is alpha over 2, not just simply alpha, and degrees of freedom is that cell. So that's the left side chi-squared table value. The right side chi-squared table value is chi-squared dot inv dot rt, and once again alpha over 2, and then degrees of freedom. So if our chi-squared calculated value is outside these limits, then we will reject the null and conclude that the variance is different from 100, which in this case is so. The test statistic is larger than the right side limit, so we have to conclude that the variance is not 100. So chi-squared is greater than the chi-squared right side value, so we reject the null hypothesis. Now when we do the p-value, okay, for chi-squared, it's slightly a little bit involved. So you have to look at both the left and the right side tail and select the smaller of the two when you have a two-tailed test. So we have to calculate both chi-squared dist of the test statistic and degrees of freedom. After the degrees of freedom, we need whether it is a probability or not. So we need to have comma 1. Okay. And then the right side value, chi-squared dot dist dot rt, test statistic, comma degrees of freedom. Okay, now rt is always probability, so we don't need comma 1. Now of course the right side and the left side tail will sum to 1, so we could have done just simply 1 minus that also would work. And the p-value is 2 times, since this is a two-tailed test, we have to do 2 times the minimum of these two, and this way we will have the p-value correctly computed. So you have to do it in this fashion. And once again, since the p-value is less than alpha, we reject the null hypothesis, and our interpretation is that we do have sufficient sample evidence to conclude that the variance is no longer 100, it is different from 100. And the probability that that conclusion is wrong is 3.7%. And that's stated here.